Okay, physicists, this is lesson 5.2. We're going to have a look at electric power. Again, we're going to have a focus on energy being found in different forms, being conserved, and having the ability to do work. Only this time we're going to bring in the idea of power, which again we're familiar with. So if we're going to talk about power, which we know already is the work done per unit time or the change in energy per unit time as it relates to electric circuits, we're going to need to link electricity more explicitly to what we know about energy. And so to do this, we're going to start off by talking about batteries again. So we're going to go back and have a look at batteries and again figure out what is happening in an electric circuit with respect to energy. So in a battery, we have electric potential energy. And that electric potential energy, we give this a new symbol, which is U sub E. And it's still it's still potential energy. When we have electric potential energy, we give it this U sub E symbol, and we measure it in joules still. And this is related to the electric potential difference, which is measured in joules per coulomb. Now, we already know that the electric potential difference is caused by the relative number of electrons at the battery's anode and cathode. And it's not a battery, it's a battery. And I just want to make a note before we go on and revisit this idea of the battery's anode and cathode and looking at the electric potential difference. I want to make a note here that the electric potential energy, or that U sub E, and the electric potential difference, which is measured in voltage, and actually this is more specifically, we're interested in the change in potential energy, and we're interested in the change in the potential difference. So really what we're interested in is the amount of work that it takes to move a charge within an electric field. And so to move the charge, we're going to have a final location and an initial location. So we're interested in the change in energy or the change in the electric potential difference. So again, these things are closely related, but they are not the same. And what's useful about knowing the voltage or the electric potential difference is that if we know the electric potential difference and we know the size of the charge, we can determine the electric potential energy. Okay, and again, this is because our U sub E is measured in joules, and our electric potential difference is, or volts, is joules per coulomb. And again, electric potential difference is the change in the voltage or the change in the joules per coulomb. Let's just make sure that we're aware of that. But if we multiply these things together, if we have a charge, so if we have a charge that we know the coulombs of as well, and in the last lesson I called this capital Q, and this isn't going to be a big deal for us. Charge is Q. It's capital Q when we're talking about the thing or the particle, the charged particle or the charged plate that's making the electric field, and it's small q if we're talking about the particle. Again, that's less important for us in physics 11. It will become important in physics 12. But if we know the charge and we know the voltage, charge is measured in C. If we multiply these things together, coulombs are going to cancel out. We're going to be left with just joules, which gives us our electric potential energy. So by knowing the voltage and the charge, we can determine the electric potential energy, or the joules. Okay, so last time we talked about that the electric potential difference, this voltage, is what establishes an electric field between the anode and the cathode, creating the conditions required for charge to move. So we had that waterfall analogy last time and said that water is not going to move unless there's a change in height, and we said that current or charge is not going to flow unless we have a change in electric potential. Okay, so not only is the voltage useful to help us figure out the potential energy here, the electric potential energy, it is this potential difference that sets up the conditions for the charges to move. And so what do we mean by that? Well, again, if we're talking about our battery here, which is sitting in our circuit, and we zoom in on this thing, okay, we can think of it much like our charged plate, where we're going to have, remember, we're going to take this thing out, this battery out. It is not connected at the moment. So it is sitting here independently. It has no way for charge to move from the negative to the positive terminal, but we are, because of a reaction down here, let me draw a little beaker and we'll show a reaction. Because of the reaction that's happening here, this redox reaction that we talked about, we are building up a surplus of negative charges at the anode. Okay, and we said it's this electric potential difference that is required for us to be able to move charges, and it's also going to establish an electric field. And we said last time that the electric field is going to go from positive to negative. Okay, and eventually this electric field is going to build up. This reaction is going to continue to happen, and we're going to keep getting these negative charges, and this anode is going to accumulate enough charges, enough negative charges, that we're actually going to stop the reaction. Now, the raw material, there is still enough raw material for this reaction to continue to occur, but this electric field is preventing that reaction from happening anymore. Now, this is really important because this is talking about how a battery actually works, because batteries maintain voltage. And we say, well, how does a battery maintain voltage? Okay, well, if you now connect, so if you have a connection now, you place this battery into a circuit. Before it was in the circuit, it just had the potential for these things to move. You place it in the circuit, you now give it the ability to move those charges around. These charges, which have all been given some energy or all have a certain amount of energy, now have the ability to move here. Okay, and so when these things start moving, it actually starts to decrease the electric field. So we're going to decrease the electric field. If we start to decrease the electric field, it's not a problem. We can actually just say, well, we'll start up our redox reaction again, and we'll start replacing those electrons. Or sorry, start replacing that charge. It's actually creating electrons, but we're thinking of it in terms of charge or coulombs. And so because of this, because when you start to move the charge, you replace the charge, it's going to maintain a constant voltage, or it's going to maintain a constant potential difference. So the voltage is always going to remain the same. So this voltage is going to remain the same for the battery. Up until the point where we do not have enough raw material, so we don't have enough raw material to continue to produce negative charge. And then what's going to happen is what we talked about last time. We're going to get an equal amount of negative charge at the cathode as there is at the anode. Our charge isn't going to flow anymore. We're not going to have a current anymore. And at that point, we say our battery is dead. Okay, now this is not going to be our focus. We're not going to look at the situation where the battery is dying. We're going to assume when we're looking at a situation that we've got a battery that has lots of raw material and it is maintaining a constant voltage. So we're going to look at this case where the voltage remains the same or remains constant. Okay, so what we can take away from this in the end is it is the electric potential difference, the voltage here, that gives each charge a specific amount of energy. So we can say that the setup here of the electric field and the negative buildup of charge at the anode, this electric potential difference gives each coulomb some energy. So now all of these things are carrying around energy. Okay, and this is important. Before these things have energy, so before they're connected and they're sitting in the battery, so before this is part of the circuit, these things all have energy. But when they're sitting in here, when they're sitting in here in the anode prior to this thing being connected, it is potential energy. Okay, so they're building up. There's this potential difference. It's giving these charged particles energy, but it can't do anything with that energy. It doesn't have any recourse yet. When we connect it, what happens to that potential energy? We start moving charge. And so if we start moving charge, what do we get? Well, in that case, when we start moving charge, our potential energy becomes kinetic energy. Okay, and again, we said we're not going to call this, we're not going to show that as electric potential energy anywhere like that. We're going to say electric potential energy like that. So this electric potential energy becomes kinetic energy when it's here. I did that reversed here. Kinetic energy. Okay. So that's great. So this is really important for us. So again, it's nice to know where that energy is coming from. It's coming from this electric potential difference. This is giving us the ability, it's giving our charge the ability to move. We know where it's coming from now, and now we can start looking at some interesting things related to power as well as Ohm's law. So in a simple circuit, if all of the potential energy given to the charges was transformed into kinetic energy, then the speed of the charges and therefore the current, which is just charge per second, would be determined by our kinetic energy equation. And we would say they would be moving at the speed that we can calculate from this equation. But circuits always have some resistance because there are no perfect conductors. Even in our best materials, our best metals for conducting charge in circuits, we are still going to have some resistance. Okay, and so this means that we always have some resistance, and therefore we are always going to lose some kinetic energy as it's transformed to light or heat. Now, this can happen just accidentally, not really accidentally, but it can happen just based on the material that we're using, or we can also take advantage of this and we can transform the electrical energy when we use resistors, things like light bulbs. So the loss of kinetic energy due to resistance in a circuit will mean that our charge slows down. So again, let's have a look. That's a lot of words. Let's actually have a look at what we mean here. Okay, so we've got our voltage, our potential, electric potential difference being created, giving our charges energy here. That energy is allowing these things to move. Okay, so these things all have some energy. And we said last time that what the resistor is doing is that it's slowing down the charge, right? So it gets to this resistor, these things get to this resistor, and all of a sudden they're going to start to slow down because the material in the resistor is designed to slow them down. So this means that they're losing energy. So let's say we'll go from big E here to little e. We've lost energy. Okay, and so just like our pipe, where we said that if we narrow the pipe, that the flow on this side is determined by the narrowest part of the pipe. The flow on this side here is going to be determined, or sorry, the flow on this side where you've got lots of energy is determined by the flow on this side where these things have less energy. And you can think of this, another way to think of this is your car might be able to go 100 kilometers an hour, but if you're sitting in traffic behind people that are only going 30 kilometers an hour, well, how fast are you going to go? Well, it doesn't matter that you can go 100 kilometers an hour, you're only able to go 30 kilometers an hour, okay? So what we can say is that our voltage, the amount of energy that we get, so let's look at this in terms of Ohm's equation, or Ohm's law, and we'll change it to this version. We're saying that the current is determined by the amount of energy given to the charges by the battery and the resistance in the circuit. So both of those things together determine how fast your current is going to flow. Okay, so you've got a lot of potential energy here. You can go very fast, but then you have this resistance. Drop in potential energy means you're going to go slower, you've got lots of kinetic energy, you're moving, so you start off by being given lots of potential energy, which turns into kinetic energy in the circuit. You are then losing some of that energy and going slower. And so that is what determines your current. Okay. So I think at this point we can now go on and we can talk about our power in our currents. Well, you know what? Before we do that, why don't we have a look at Ohm's law? So this is one version. We explained this pretty well. We explained how voltage and resistance set up our current. But maybe we should have a look at our other equations or our other variations of this equation. So let's look at it this way as well. If we're in the case where we've said we've got our constant voltage, so this is going to stay the same. Let's space these out a little bit, where our voltage is going to stay the same because we always have the same voltage from this battery. Well then, if we increase the resistance, what has to happen to our current? Well, we must slow it down. If we have the same thing and we decrease the resistance, and this stays the same, then what's going to happen? Well, our current's going to speed up because we're not going to lose as much energy when we decrease the resistance. Here we're losing more energy because we're increasing the resistance. Okay, so now we can go on and talk about power in our circuits. And so now that we've designated the electric potential energy as U sub E, why don't we rewrite our power equations? So we can say that we know power is equal to work over time, which is equal to, and instead of saying change in potential energy, we'll say change in electric potential energy over time. And we already said that our change in potential energy is equal to the change in our potential difference times our charge. Now again, we've said we don't really keep these things in, so most of the time we look at this equation, it's going to look like this, and we just know that we're talking about the change in, so we'll take those out. And if we do this, if we plug this into this equation, well then it becomes power is equal to our voltage times our charge over time. And look at this. That is just power equal to our voltage. Charge over time, well, that's current. Okay, so this is a new equation that you are going to get on your formula sheet. And this, in combination with Ohm's law, we can do a few different things with. Okay, so we know that power is equal to VI, but we also know that I is also equal to VR. So we could say V times V over R, and we could say power is equal to V squared over R. We also know that V is the same as IR, so we could say I times IR, and we would get I squared R. Now you might want to stop right there and say, well, hold on a minute. If we look at these two power equations and we look at the relationship with the resistance, we say in this first equation, it looks like we've got an inverse relationship such that if we increase the resistance, we are going to decrease the power. Okay, so this is our amount of potential energy per time that our circuit is able to produce. And here it looks like if we're increasing resistance, we're actually going to increase power, which again is the amount of energy we're able to produce per unit time. So this looks like we've got a bit of a problem, but in fact we can explain this relatively easily. So the power converted in a circuit by something like a light bulb, a resistor. So let's put a light bulb in here this time. So there's going to be some resistance in this light bulb. We're going to have some amount of voltage here, and we're going to have a current of charges flowing. And the power converted by this resistor, the light bulb, per unit time is going to decrease if the resistance in the circuit increases. So we can actually rationalize that quite easily. If we increase our resistance here, then what is that going to do? Well, it's going to slow down our charge. So that means that we're going to have, if we slow down our charge, then we're going to have less energy flowing per second because we've slowed down our charge. So our voltage, we said, is going to stay the same. And in this equation, voltage is going to stay the same. But what's going to happen is when we increase resistance, we are going to slow down this charge so that we've got less energy flowing per second. So that means we're going to have a decrease in power. All right. So if we decrease the power, that means our I, this I must decrease, right? We said our flow is going to slow down if we increase our resistance. And if we look at this second equation, because the I here is squared, because this I is squared, the decrease in the current offsets the larger resistance, and in fact the same amount of energy is going to be transformed by the resistor, the light bulb, per unit time. So because this resistance increases and decreases the current, that decrease in the current and the fact that this is current squared is going to offset the increase in resistance. And that explains how we can have what looks like contradictory information here with our resistance and our power. Okay, you don't really need to worry about that too much. It's nice to know why that's happening. What we really need to be able to do is to be able to create these equations. So let's write them a little bit more neatly over here. This is the one you're going to get. And here are the ones that you should be able to derive. So again, let's say this one is on your formula sheet. And these ones you're going to need to use Ohm's law. Okay, let's go down and have a look at a couple of examples here. So here we have an electrical appliance that uses 1 times 10 to the 2 watts when connected to a 1.2 times 10 to the 2 volt power line. what is the resistance in the appliance? So let's write down what we know. We've got a power given to us. We've got a voltage given to us. And it wants the resistance. We want to figure out what is the resistance. Well, in our power equation that I said that we would have, so here in our power equation, we don't have resistance. We've got voltage and we've got current. So we're going to want to keep our voltage, but we need to get rid of this current. So we bring in our Ohm's law. And we say, well, we'll make up an expression for current, which is going to be the voltage over the resistance. We can plug that in for I in the equation. V squared over R. So now we can say we've got 1.20 times 10 to the 2 volts all over top of, oh, sorry, before we do this, we're looking for that resistance. So let's switch this equation around again. So now we're looking for resistance. So with some algebra, we're going to turn this into V squared over P. And let's just call these, that 1.2 times 10 to the 2 is 120 volts. And we're going to square that. And the power is 100 watts. And so in the end, our resistance is going to equal 144 ohms. And are we good with sig figs? Yeah, it looks like 3 sig figs there. So here's our answer. And there's our answer right there. Yeah, looks good. Okay, question 2 here. An electric hairdryer uses 1100 watts of power. What current is drawn when the hairdryer is connected to 120 volts? Well, we know our power. It's 1100 watts. And we have a voltage of 120. And we want to know the current. Well, we just saw this equation. So this all looks good. We just need to be able to rearrange for I. So our current is going to equal our power over our voltage. Okay, so we've got 1100 watts over 120 volts. And that is going to leave us with 9.17 amps. And again, ambiguous here about our sig figs, but we'll say that zero will assume that zero is significant. Now, the second part of this question is saying, what is the resistance of the hairdryer? Well, what do we know? We've got a voltage. We just figured out a current, so why don't we just go ahead and use Ohm's law, where we rearrange for resistance. And we will say that we know our voltage is 120, and we've got 9.17 amps. Okay, and so that should leave us with 13.1 ohms. Again, to 3 significant figures. Yep, looks good. Okay. Now, if we go down, there's a question where we need to interpret a graph. And again, this is something that we need to be comfortable with for any graph that we're given. So let's do a little bit of practice here. And I don't want to tell you the answer, but I'll give you a hint. So a power supply was connected to a resistor, and a student plotted the graph of current, which is I, measured in our current is I, which is amps, flowing through the resistor versus time t as shown below. So important for us to remember from our last lesson that our current, which is measured in amps, is really the amount of charge in coulombs going past a point in seconds. So it's the amount of coulombs per second. So if we say, if we're looking at the area here, area under this graph, now if we go slope, which is rise over run, So rise is going to be current in amps over time in seconds. We've got amps per second, and that's not something that's really noticeable to us right off the bat, even if we change this thing to our amps, if we change it to our charge per time or our coulombs per second over top of time in seconds, we're going to invert and multiply, so it's going to give us coulombs per second squared. Again, not something that we're really familiar with. So slope doesn't do much for us here, but area, it's asking us to find the area under the graph. So if we're doing area, what are we actually doing? And I'm going to leave you there because that should be a pretty good hint to get you started. So you can try the rest of these example questions on your own, and then you can do homework. I'll put it right at the bottom here. You can do this formative assessment for homework, which shouldn't take you too long. And then we're on electric circuit 01 for homework.